Hi, my name is Sanjina Ahmed, and I am currently in my fourth undergraduate academic year at Wayne State University, studying mechanical engineering. I will be solving a heat transfer problem from the Wayne State University course of ME 4210, and the current professor for the course is Mahbub Islam. To read the problem statement, the temperature distribution across a wall is 0.3 meters thick at a certain instant of time is T of x equals A plus BX plus CX squared, where T is in degrees Celsius and X is in meters. A equals 250 degrees Celsius, B equals negative 200 degrees Celsius per meter, and C equals 30 degrees Celsius per meter squared. The wall has a thermal conductivity of 1.0 watts per meter Kelvin. So for part A, on a unit surface area basis, determine the rate of heat transfer into and out of the wall and the rate of change of energy stored by the wall. Part B, if the cold surface is exposed to a fluid at 100 degrees Celsius, what is the convection coefficient? So to begin, we know our thickness is 0.3 meters, and we have our T of x here listed out, and each of the values for the T of x, A, B, and C. Our thermal conductivity is also provided. So using all this, we can create our schematic to help us solve this problem. So here we have our Q in, and we also have our Q out, Q being our heat transfer, of course. And this surface here is our T of x. And our wall thickness, it was defined to be 0.3 meters. As for our assumptions, we can assume that it's in a steady state, it's one-dimensional, and there's no mechanical energy generation. Moving on to solve for part A, we can plug in whatever is given as our A, B, and C values. To continue, we need our conservation of energy of control volume formula, which is the following. So the EST is our stored energy. En is defined to be our inflow of the energy. E out is our outflow. And Eg is our mechanical energy generation. But since we are assuming that there is no mechanical energy generation, we don't have to worry about this. To solve for our inflow and outflow, we can use our Q conduction formula. Since area is not given, we can simply make sure area is kept on both sides so that it cancels out. So here, Q conduction or heat transfer rate, K is given as our thermal conductivity, and we must take the derivative of our T of x function right here. So taking the derivative, we have negative 200 plus 60x. And at position x equals 0, as indicated here, heat is transferred into the wall. And that gives us our energy inflow being 200 watts per meter squared. In order to solve for our energy outflow, we'll be using the same formula as here, except our x position will be at x equals 0.3 m, since that is where the heat is being transferred out of the wall. So our outflow of energy is 182 watts per meter squared. As for our stored energy, it is simply our inflow of energy minus the outflow of energy, using what's given here. So our final answer for part A comes out to be 18 watts per meter squared. Moving on to part B, in order to solve for our convection coefficient, the Newton's law of convective cooling gives us Q equals HA T surface temperature minus T free stream. H being our convection coefficient, A being our area, our surface temperature here, and our free stream temperature. So right now we know that our free stream temperature is 100 degrees Celsius. So we must solve for our surface temperature. And to do that, we simply plug in everything that's given into our T of x formula. Specifically, x equals 0.3 meters. At T of 0.3, we get 192.7 degrees Celsius. So we can simply plug this in to our formula right here in order to get our convection coefficient. And from part A, we know that the outflow of energy is 182 watts per meter squared. So we will be using that as our heat transfer rate. Solving this out, we get our convection coefficient to be 1.96 watts per meter squared. And that is the end of the problem. Thank you for watching, and good luck.